This section of the class we're going to talk about using integrals to calculate volume. Okay, now so far I've told you that integrals represent an area, and they do. But you'll find out here in a minute that you can also use them to calculate the volume. So formulas that you're familiar with from geometry and stuff like that, like the volume of a sphere is 4/3 pi r cubed, that can all be derived from calculus. In fact, it all was derived from calculus. And so calculus, using these integrals, you can generalize them to calculate volume. And I'm just going to work a couple of quick problems to show you the principle involved with that. But before I do that, I want to give you a quick explanation of how you can do this. Okay, let's say you have, x, y, like this. This is the x-axis, obviously, and this is the y-axis. And you have some function here, okay? Some function. Let's call it f of x, right? Like we always do. And it's defined up here above like this. Now let's say that you took this f of x and let's say you rotate it about the x-axis. So let's say you have some piece of cardboard here that's in the shape like this, and then you rotate that cardboard all the way around. Like if this piece of paper were up here, you'd rotate it around like this. Well, then what you would have is you'd have something like that, fairly symmetrical like this. Okay? And then, just to give you a little bit of dimension involved, I'm going to try to draw it in 3 dimensions, and I'm not going to do probably the best job. But it would look something like this, and over here you'd have this. Okay, well, obviously it would be going around like this, and then you'd have something like this, and it'd be kind of on the other side, it'd be kind of going around like this. So this is an example of how you can take a curve and by rotating it around an axis, arrive at some volume. Now, it would be very difficult to calculate the volume of this vessel here. Okay, you could fill it with water, sure, and you could figure out what the volume is experimentally, but if you wanted to measure it or to calculate it using calculus or regular old math, it would be really difficult to do because it's got this nice curve to it, and this curve could be pretty complicated. So how do you do that? Okay, well, if you think about it, okay, the distance, by definition, the distance between here and here, what is this distance? Well, this is just simply f of x. That's by definition what it means. At every value of x, this is f of x, and over here this is f of x, and over here this is f of x. That's what the function does. It tells you what the value of f is at various values of x. Okay? So if I were to look at the area, forget about volume for a second, if I were to look at the area of this little slice, let's say I slice it right here, and I'm interested in the area. The area, what's that going to equal to? Well, in general, this is a circle, right? Because you've rotated it around in a circle. So the area of a circle is just pi r squared, right? That's the area of a circle. But I know what r is. This is the radius, because over here, this would be a radius. So the area would be pi times f of x squared, right? Okay, this is f of x. I rotate it around. It defines a circle in the cross section. So pi f of x squared, that's going to be the area of this slice. Now, don't you remember back when I told you what integrals really were? They calculated the volume, but I said if you have an integral of blah, 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 blah over dx, what you're doing is you're taking these little slices of a graph, and you're letting the slices become really, really, really thin, and this integral is adding them all up. Okay? Well, it turns out you can do the same thing on a bigger scale. I'm going to tell you what the answer is, and then we're going to talk about it. The volume of this vessel can be defined by an integral. Okay? From A to B, where in this case this could be x is equal to A and this could be x is equal to B along the curve, okay, of the cross-sectional area over dx. And I've already calculated for you what the cross-sectional area is. It's pi times f of x squared dx. And this is if you rotate about x-axis, right? Now, how can this be? What this inside stuff means is if you slice one of these things up, you will get an area like this. But what this integral is doing is it's taking all of these little cross-sectional areas, there's an infinite number of cross-sectional areas here, and it adds them up. And it turns out, the big picture here is, What does volume mean if you have a volume of a square? All you have to do to find volume is you take the cross-sectional area of this one, you add it to the one right underneath, you add up all these little cross-sectional areas, and that's how you get the measurement in this new direction, in this new dimension. And by adding up an infinite number of cross-sectional areas, you get what we call the volume. So here you define the cross-sectional area by this, and this integral is the mechanism that you use to add them all up. Okay? So that's very simple. It's how you get the formula for the volume. Now, if you were going to rotate it about the y-axis, if you had some function here and you wanted to rotate it about the y-axis, it would be very similar. You would integrate from c to d, which again are just numbers, okay? And that would be pi times g of y squared dy. So basically it's a function of y, and then because you want to know the function, as the radius would be defined in terms of the function going out from y, you'd square that, and then you'd be integrating along the y-axis. It's actually the exact same formula here. It's just the formula itself would be derived differently. So this all looks fine and dandy, okay, and great, and hopefully you understand what I mean by that. But I just want to work a couple of quick problems to show you how you might go about and calculate the volume of something using an integral. Okay. What if you had f of x is equal to the square root of x? Okay. And you want to rotate it about x-axis. Okay. And then you want to go from x is equal to 0 to x is equal to 1, and you want to find the volume of that. Well, let's draw a quick picture, because pictures are always worth 1,000 words, right? The formula for this is f of x, and this is x, looks something like this. Okay? This is the formula, but you're rotating it about the x-axis, so really what you're going to end up doing when you do that is you're going to have a symmetrical thing here, and it's going to go like this, right? So what you're finding is the volume of this kind of bucket thing, like that, okay? So then the volume is going to be the integral from x is equal to 0, and then this right here, x is going to equal 1. That's why it says from x is equal to 0 to 1. So you're going to have 0 to 1 of pi times f of x squared dx, that's our formula, which is the integral from 0 to 1 times pi. F of x is this, like this, squared, because it's pi r squared, dx. Okay? And then the volume is going to be equal to integral from 0 to 1, basically, of pi x dx, because the square of a square root, they go away, they cancel each other. And you know how to integrate this. You don't even have to do any substitution or anything. You just say, okay, well, this is pi over the exponent plus 1 is 2 times x squared. Exponent plus 1 gives me that. And don't forget to evaluate from 0 to 1. Okay? So then the volume is going to equal pi over 2. This evaluated at 1 is going to be 1 squared minus this evaluated at 0, 0 squared. And you can see this is going to be 0 and this is going to be 1. So the answer is pi over 2. So now you've calculated the volume of something, and all you need to know is the function that defines its sort of its shape, and then you're saying you're rotating it about the x-axis. Now obviously this has its limitations. It can only let you calculate the volume of things that are kind of symmetrical, because then you can define a shape and then you're rotating it and it's symmetrical. It can't let you calculate the volume using this method of arbitrary blob, but in principle it does let you calculate some things, and most calculus courses definitely cover it, so I wanted to give you that. Now I'm going to do just one more quick problem to kind of illustrate a little bit more detail. What if you had, and I'm just going to kind of draw this picture here. What if you had a line, and this is the line, y is equal to x, okay? And then you also had a curve that went up like this, and this is y is equal to x squared, okay? So the problem might say, the region bounded by the lines y equal x and the curve y equal x squared, well that region is defined right here, like this. This is the region. Rotate that region about the x-axis, like this. Okay? So rotate the region around x-axis. Okay? And then you define a volume. Now this region, this intersection here is at 0, 0, and this intersection here is at 0, at 1. It doesn't really matter the y value of it, but the x value of this intersection is at 0 here, and the intersection here is at 1, and I think you can convince yourself of that by looking at those two equations there. You can solve the system of equations and you'll find out that they intersect in those two places, and I sort of drew it for you so that you kind of know. And if you put x is equal to 1 here, okay, you'll get a y is equal to 1 out of this equation and a y is equal to 1 out of this equation, so they're definitely the same point. Okay, but let's say you had this region defined by these curves and you rotated that region, so it's going to be a really weird shape, but how would you calculate the volume? Well, the way you do that is the volume is going to be from 0 to 1, x is equal to 0 to x is equal to 1. Okay, and what you have here is you can define it in terms of this curve minus this curve, right? So what you can say is you can have pi times this function, x squared, minus pi times this function, squared. Let me just write it like this and I'll explain it. What you're doing here is, you know, if you find the area under this, the volume of the function defined by the rotation of this line, you'll get a big number. And if you take what's left over from the volume underneath this curve and you subtract the two, what'll be left is going to be what's in between them. So you're finding, really, when you do this part, you're finding the volume of what you would have if you rotated only that line, which would be a pretty big volume, like a cone. And then this one is the volume that you would have if you had just this curve rotated around, which is going to be basically this area underneath the curve, rotated all the way around. But you're not interested in that. You're interested in the difference between them, so you just subtract them, like this. So in order to proceed, you just have integral 0 to 1 of pi x squared minus pi x to the 4th dx. You just multiply those exponents there. And then over here you'll have pi over 3x to the 3rd when you do this integration, pi over exponent plus 1, x the exponent plus 1, minus pi over 5x to the 5 for the same reason, the exponent plus 1 here and here, evaluated from 0 to 1. Okay, so then in the end what you're going to have is pi over 3, and you're going to evaluate this at 1, right? Well, this is just 1 cubed minus pi over 5 times 1 to the 5th. And I'm going to subtract off this whole thing evaluated at 0, but I can tell right away 0 is going to go here and 0 is going to go here and the whole thing is going to go 0. So I'm just going to not even bother writing all that stuff down. It's going to go to 0 for the second term. And since this is 1 and this is 1, you just have pi over 3 minus pi over 5. And you can simplify that fraction and you can get, in the end, if you do that, you'll get 2 pi over 15 if you do that subtraction. But you could simply leave it like this and that works just fine.